Okay, I think it's now time to start our today's quantum seminar. Welcome, everybody. At the beginning, I would like to introduce you briefly, our speaker, Professor Ralf Röhlsberger studied physics at the University of Hamburg, where he received his PhD in experimental physics in 1994. After completing a postdoctoral appointment at the Advanced Photon Source at Argonne National Lab, he was scientific assistant at the University of Rostock, where he habilitated in 2002. In the same year, he received the Innovation Award, Synchrotron Radiation of Basis Storage Ring. After an interim professorship at the Technical University in Munich, he has been since, I think, 2003, a senior scientist at DESY at Hamburg. And he was also a deputy leader of the Experimental Facility Division at the Petra 3 Synchrotron Radiation Source Project. Since, I think, last year, Professor Röhlsberger has been at the Helmholtz Institute, Jena, one of the directors, and also at the Institute of Optics and Quantum Electronics at the Friedrich-Schiller University, Jena, where he holds the chair of X-ray physics. His research interests include the development of novel X-ray scattering methods, nuclear resonance scattering, physics of thin films and nanospectors, magnetic properties of low-dimensional systems, and so on and so forth, X-ray quantum optics. So the list is quite long. I will skip this. Similarly, I have not mentioned too many awards, but the list of awards and fellowships is also long. Professor Röhlsberger, we are delighted to have you with us today, and we'll look forward to your talk. The title is shown there, When X-rays Go Quantum, from Cavity QED to Quantum Imaging. The floor is yours, please.
Yeah, thank you very much, Mustafa and Arne, for this kind invitation and also for the introduction to this colloquium. And yeah, I'm very, very happy to give that colloquium, although I would have liked to travel to Mainz, where I actually have never been before, I have to admit. Maybe this can be realized in a later occasion also for a personal visit. Yeah, so let me start with the talk, When X-rays Go Quantum. First, a few words to the background of this slide, as I briefly talked about in the discussion before the start here. So this is not Jena, of course, as you might guess, but this is actually the place where a lot of inspiration came during the past 10, 12 years on the research field I'm going to talk about today, namely X-ray quantum optics. And many ideas were actually born in these PQE conference series, Physics of Quantum Electronics, that are every year organized by Marlan Scully and co-workers. So this was my first conference where actually I met Marlan Scully first, and here are some other students and colleagues who I worked together with after that conference. And it's a habit of Marlan Scully, or was for a long time actually. I think many of you know him, or some of you perhaps also have been on one of these conferences. They are quite famous and well-renowned in the field of quantum optics, quantum electronics, and so on. And Marlan often had, in the first years when I attended these conferences, single-author PRL manuscripts that were just accepted somehow, and he was running around and advertising this to other people, inviting them for the lunch table and to discuss. Yeah, he likes to discuss and find co-workers, collaborators, and so on, and start new projects. And this paper actually that was then published soon after that conference actually inspired me to think about how could we perhaps measure the collective lump shift that single photon superradiance experimentally. So this was a series paper actually, and I hope I can convey to you during this colloquium talk why I thought about this, why this was so intriguing for me. And yeah, let's start with actually the basics, how X-rays can go quantum. First of all, the X-rays or any other maybe classical field couples to quantum systems like atomic energy levels. I mean, these are immediate quantum states one can think about. And so there are actually two blobs here on this slide symbolizing the structure of an atom. So first of all, the electron shell with binding energies ranging from kiloelectron volt to the core to electron volt at the valence electron level. And we all know that optical laser fields all the way up to soft X-rays or even harder X-rays can be used to address these levels, control and probing the dynamics of valence electrons and the outer shells, or hard X-rays to excite or ionize core electrons, right? And I think in Mainz you also will guess what this the bottom is here, the blue circle with energy levels from the mega electron volt regime to the kilo electron volt regimes. Correct, this is the nucleus. And it also has electromagnetic levels formed by the coupling of the nucleons inside the nucleus. And mega electron volt, these are very hard X-rays, gamma rays to excite nucleons in the nucleus. But there are also low-lying levels, low-lying compared to the mega electron volts. And those are the Mössbauer isotopes. Yeah. Also, think and hope that you are aware of what Mössbauer isotopes are. I mean, these are exactly those nuclei with low-lying electromagnetic levels, which actually leads to recoilless absorption and emission, because the recoil energy of such a photon, a kiloelectron volt photon, would be emitted from a nucleus bound in a solid. That is an essential prerequisite for the Mössbauer effect. This can be emitted with a very high probability recoillessly, yeah, from a strongly bound system. The whole solid basically acts as a recoil partner. That means that the recoil energy p squared over 2m is really negligible, because the recoil energy, this is basically then much smaller than phonon energy. So the emitted photon has no chance, or the recoil has no chance to move over into to be dissipated in phonon excitations. That's why we have these large amounts of, or large fraction of recoilless absorption and emission. So that means you can really have a complete energy conservation. That means a photon that is a gamma ray that is emitted from a nucleus can be reabsorbed by the same nucleus somewhere else, by a similar nucleus somewhere else. That is the essence of the Mössbauer spectroscopy. Since the nucleus is isolated from the environment so nicely, you really observe the natural line width that can be very small, say from the pico to nano electron volts. And I will talk about this later on this slide, for example, here, just to set the stage for this talk, what the atomic levels we are dealing with are. These are the electromagnetic levels of Mössbauer isotopes that can be really considered as almost ideal two-level systems. And in case of the most famous, most widespread used Mössbauer isotope iron 57, here we have a typical Mössbauer spectrum that looks like this. If you have a radioactive source here that emits isotropically, and you want to select or to illuminate a small sample and filter out a angular section of this emitted radiation here directed onto the sample and recorded by the detector, you can, for example, record such absorption spectra, these six very narrow resonance lines with a width of about 5 nanoelectron volts. They constitute a very sensitive probe of solid state properties of the solid where these iron nuclei are embedded in. So the energy tuning here for the spectra, that goes along with the Doppler motion of the source that is moved back and forth, and the Doppler detuning actually allows us sampling of this energy scale here. Of course, this radioactive source emits into 4 pi. You select only a very tiny fraction of this whole solid angle, so you're ending up in a count rate, in a signal rate of photons going through your sample of maybe 1 photon per second. Yeah, and so this such spectra with with a very good quality from small samples. I mean, often you have samples only in a small quantity, can take days. Yeah, and the whole situation changes, however, and this is a development that was started in the 70s, basically of the last century, when it was realized that synchronous radiation has a brilliance intensity per solid angle that surpasses that of radioactive sources by orders of magnitude. So the radiation of a synchrotron radiation source is emitted in a already very collimated fashion. So where almost the whole radiation along one direction is already collimated in this angle here, horizontally, vertically and horizontally it's a bit wider, but nevertheless you can obtain count rates of 10 to the 5 photons per second to record not energy spectra, but this pulsed synchronous radiation converts Mesmer spectroscopy onto the time domain, which is basically where you record the delayed response, the decay, the temporal evolution of the decay after excitation of these nuclear resonances at time 0. So you observe the delayed response of your iron 57 nuclei in the sample, which is in this case this quantum beat pattern. You can watch it as a Fourier transform of this energy spectrum shown here. You get a beating, temporal beating, from which actually you can derive solid state properties of the host matrix where the iron atoms are embedded in. So it looks like here again, the synchrotron, you have the sample, the radiation passes through, you have these very short pulses, 50 picosecond long, separated by 200 nanoseconds. That's where actually these spectra, these temporal beat patterns fit in. And with timing electronics, you can record these patterns with sub-nanosecond resolution. So, there have been, after establishing this method in the 80s of last century, there were a multitude of applications in magnetism, nanoscience, geophysics, biophysics, all those disciplines where you encounter often very small sample volumes. For example, in geophysics, where you can probe in high pressure environments, tiny samples under extreme conditions. In magnetism, nanomagnetism, especially thin films, very small magnetic particles, or biophysics, single organelles in biological tissue can be probed. This enormous, these outstanding properties of synchronous radiation have led to a number of applications also in fundamental science, and that's where actually I will focus on today. Just a concluding slide on my introductory part. How does there's a little animation here of nuclear resonance scattering of synchronous radiation. So where do these quantum beats come from? These temporal beat patterns. That they come from the fact that the nucleus, the energy levels of the nucleus, they split in a magnetic environment through the nuclear Zeeman effect, basically the ground state in 2 levels, the kinetic state in 4 levels here, and the dipole selection rules, they dictate that you get then 6 allowed transitions here. on this resonance here, 14.4 keV. The lifetime is 140 nanoseconds, very convenient for recording and detecting, and the energy width is about 5 nanoelectron volts. So when a pulse of synchronous radiation comes from the left, yeah, so it virtually excites all Mörs-Bauer nuclei in the system. So the synchronous radiation is really broadband. You excite all these resonances at the same time, and the nuclei, they re-radiate. They radiate actually at these frequencies, at these transition energies. I have just picked three frequencies here: omega 1, 2, and 3 out of these 6. And what happens then is that in the far field, or in the emitted radiation, you get a superposition of these frequencies. So two different frequencies, they yield a single frequency beating. Yeah, so you see that here in the Maury pattern. And this frequency beating, it gets more complicated the more frequencies you superpose. And if you take all 6 transitions here, you get this beat pattern that I had shown on the previous slide. So that is actually the essence of this method. You can take these beat patterns now as a fingerprint, for example, of the magnetic structure of the sample, because these relative intensities, they depend on the relative strengths with which these transitions are excited, and the relative strength is then determined by the orientation of the magnetic moments in the sample, for example, which constitutes a very sensitive probe for magnetic spin structures in thin films, for example. But this is not what I want to dwell on here during this talk. I just wanted to give you an impression what the basic method is that we are using. We're using these iron 57 nuclei as a 2-level system to probe the fundamental aspects of the collective light-matter interaction in the X-ray regime. So this is a method. I mean, the principal experimental method is well established at many synchronous radiation sources around the world, and also X-ray lasers. So we can really build on these experimental capabilities to perform the experiments I want to talk about today. So let me outline my talk. What follows, actually, I want to briefly talk about the properties of X-rays from accelerator-driven light sources, then explain you how these new light sources enable new science, namely the many-body physics of the light-matter interaction, and especially talk about what comes out of cooperative emission in X-ray cavities. That is a central element here that I'm going to talk about today. Cavities for X-rays, and that's actually the playground, the environment in which we have observed phenomena like the collective lump shift that actually Malan Scully inspired me to look for, and electromagnetically induced transparency, or even towards collective strong coupling. And if time is still permitting, I would talk about also intrinsic correlations and quantum imaging. Okay, so yeah, this is actually a diagram of the brilliance of radiation sources, in principle, as a function of energy. So we have here a large range extending from the visible into the very hard X-ray regime. So here you see laser sources with the brilliance, photons per second per solid angle, per source area, and per energy interval, which is 0.1% of the bandwidth. So this is the figure of merit for these accelerator-based radiation sources, because you can imagine that in this narrow bandwidth that we are that the nuclei are offering, we need to have enough photons actually to do experiments with. So how many photons we have in 4 and 5 nanoelectron volts? I mean, it turns out that these are quite many actually, and this is actually these are typical diagrams how to estimate the performance and the possibilities one can exploit with the radiation source of a given type. Let it be synchrotrons here, or what is shown here is the peak brilliance of X-FEL free electron lasers around the world, from the soft X-ray to the hard X-rays. So so there we have 9 orders of magnitude in between. So this will open up a number of possibilities that are unthinkable with synchrotrons, for example. So the temporal development, I mean, these sources have been developed over the past decades. The synchrotrons actually and lasers, they superseded X-ray tubes by far with respect to this property here, going from the 2nd generation sources, 3rd generation to 4th generation sources, which is shown graphically here. So we have the 2nd generation synchrotrons. These are basically where radiation is generated from bending magnets, where electrons are deflected by magnetic fields, and then synchrotron radiation is generated. In 3rd generation sources, we have periodic magnetic structures, so-called insertion devices, like undulators or wigglers, that then generate much more intense and directed beams of X-rays tangentially to the orbit. These sources are currently the most used ones around the world, because they are really have been optimized for a number of experiments in all kinds of the natural sciences. And over the past 1 or 2 decades, the 4th generation sources, the X-ray lasers, came up. So we have a completely different generation principle, the so-called Sashes, self-amplified spontaneous emission, where such a periodic magnetic structure is then used, and highly directional electron beams from linear accelerators are passing through these periodic magnet structures to generate even more intense, fully coherent beams for these experiments. And they actually offer properties that I may remind you of later for probing fundamentals of the light-matter interaction in completely new regimes. So the example is, I show this here just briefly, the European X-ray free electron laser in Hamburg that has is operating now since already more than 4 years in user mode, which is a 3.2 kilometer long structure starting here at the DESY campus, going all the way to Schleswig-Holstein, where the experimental hall and the headquarters are located, with underground beam lines here and experimental stations here in the basement of this building. And this is how these linear accelerators that are feeding the undulators to generate these highly brilliant beams, this is how they look like in these tunnels. All superconducting modules, actually cavity modules, where the electron beams are going through and are accelerated before they go through the undulators. And after the undulator section, I mean, there are photon beam lines following, where the photon beams are then configured actually to be directed onto the experiments here that are then following here on the left behind me, basically. So yeah, this is actually where we are today. In principle, this diagram shows actually now more specific to the application with nuclei, with iron 57 nuclei, the number of resonant photons per pulse that we can expect. Yeah, and you see here the enormous increase from 3rd generation sources, 2nd, 3rd generation synchrotron radiation sources, where we have at most 1 photon per second in a bunch, yeah, or one resonant photon per bunch that is generating radiation. So only the high rep rate of these sources actually brings us into a regime. When we have, say, 10 to the 6 pulses per second, then you can imagine that we have a considerable fraction of photons coming from these sources onto the experiment. But here we, with the X-ray lasers, or even an advanced version, the X-ray oscillator, may generate radiation pulses where we can do actually full experiments with the photon content of single pulses. And this is actually a really intriguing possibility for future experiments. So you see how far we are from radioactive sources with these accelerator-driven X-ray sources for addressing nuclear resonances. And so, yeah, this is the IM57 resonance line in principle. That is our working horse. 4.7 nano EV line widths. There are, of course, other Mörsbauer isotopes around that fall into the regime that can be addressed at those beamlines that have been already explored to some degree. Of course, IM57 is so popular because it has the highest resonant cross-section, but there are other isotopes that are also interesting for fundamental experiments. I think I don't have to mention the notorious 229 thorium, which is actually a nucleus with a resonance in the ultraviolet or EUV regime. This perhaps has to be updated. There are new numbers, I think more precise ones. But you see the enormous relative line width here that is offered with potential applications here as atomic clocks. There's also a candidate in the hard X-ray regime, scandium-45, 12.4 kiloelectron volts with a relative line width. Not too far actually from this thorium-229. So there are interesting candidates also for fundamental experiments. Yeah, in general, I mean, having said all that, I hope I could give you a flavor a little bit already that new light sources enable new science in this field, and especially with regard to the many-body physics of the light-matter interaction. So we have the ingredients. The main ingredients are indistinguishable field quanta, photons, if we prepare them properly. And then we have matter quanta, namely atoms, atomic emitters. And if we bring this together with a photon field of high degree of longitudinal coherence, together with an ensemble of identical atoms, like shown here, we can explore what we call quantum cooperativity of light and matter, where actually we use this combination actually to enhance quantum field effects through collective interactions between identical atoms. So if you really have identical atoms here that are really indistinguishable, I mean, you have to treat them as a giant atom, and then you are basically in a completely new regime of the light-matter coupling. So experimentally we have on the one side here, on the photon side, we have these high brilliance sources with a high photon degeneracy, many photons per mode. On the other side, here on the sample side, we have identical atoms of Mörsbauer nuclei where we can control the hyperfine interaction very precisely. For example, to make sure that we have really two-level systems. So, yeah, then of course we are interested in what are the properties of a multi-photon collectively excited state. Before we do that, before we can solve this question, we need to understand what a single photon, what happens to a single photon if it excites an ensemble of identical atoms. So what happens if such a photon is absorbed here by this ensemble of atoms? We get this quantum state actually. That's a so-called single photon timed Dicke state. That is how this state is called in the literature now, where actually one atom is excited, this arrow up here, and the others are still in the ground state. But we don't know which atom is excited, so that's why we have to have this coherent sum with the spatial phase factor here of all these Fock states, where one atom is excited and all the others are in the ground state. Yeah, and if you analyze this, you find that this, it's classically, one can look at this as a system of n-coupled oscillators. And this turns out not to be an eigenstate of this system, not a radiative eigenstate. That means that many modes with different resonant frequencies and different decay times are populated, and they all radiate and give rise to these so-called propagation quantum beats. So it's not an exponential decay here, like you would expect from a single nucleus, but it is rather a superposition of all these radiative eigenstates of n-coupled oscillators that give this pattern here. Yeah, and it's, if you analyze this further, I mean, due to the spatial phase factors, it's clear that geometry plays a decisive role, can change the physics fundamentally. And yeah, so let's explore special geometry to cut the story a little bit short. So let's assume that we have, for example, a system of nuclei here sitting as a thin layer on a surface. And yeah, so what is the case here? So how does this state look like for an arrangement of atoms like this? And so we eliminate this layer, this thin layer of nuclei on the surface with the radiation field Kn, and we have a reflected field. X-rays can be totally reflected from this surface. We have an outgoing wave vector, and we have these atoms at different positions. And if you calculate the spatial phase, the phase with which the outgoing radiation is emitted, the spatial phase between those two atoms is basically this quantity, the difference of the wave vectors, that is the momentum transfer basically, and this is the difference of the spatial wave, the position vectors. Those two vectors here, these difference vectors here are perpendicular to each other, so the relative spatial phase is basically zero. Yeah, and so now we know that there are no relative spatial phases to be considered in this geometry. We can enhance the light-matter interaction actually by not putting these atoms on the surface, but in a cavity between two parallel plates that are totally reflecting the X-rays. And so we couple our photon fields now into these cavities, for example, evanescently, to this very thin layer, and the top cladding, so to say, and then we form standing waves in this cavity, and it greatly enhances the light-matter coupling of the nuclei and the photons inside this cavity. Still no relative phases due to this geometry between the emitters. And what we can achieve, intensity enhancements by 1 to 2 orders of magnitude inside of the cavity compared to the incident amplitude. So that is actually how such an X-ray cavity look like. These are a few nanometer thin layers of palladium carbon where this iron is embedded as an almost X-ray transparent material, and the palladium cladding as a top mirror. And now actually our time decay state turned into this expression here, where the atoms all have the same spatial phase factor here. So you can pull this in front of the sum, and we actually have now a realization of the so-called small sample limit of decay superradiance. So that is actually really an important, very important fact now, because this ensures that we can really excite a radiative eigenstate of that system here. So we don't have these relative spatial phases, and that is important. We have actually an environment in which we can prepare radiative eigenstates of a collection of identical emitters. And that is the essence, actually. Now we can investigate these radiative eigenstates. We can measure the decay time, the decay constant. We can measure the energy, the collective energy, so to say, the collective resonance energy of that system, namely the collective Landshift. So theoretically, I mean, we can derive these properties. How does the cavity change these quantities? How does the cavity change the radiative properties? So we sum up, we treat this this diagram here, which actually is turned upside down here. Here's the cavity, here's the two claddings, here's the iron 57 layer embedded, and we couple in here the radiation that is multiply reflected between these cladding mirrors, and sum up all these partial waves. Yeah, you do this in geometrical optics also, and we just add those properties here, taking into account the various parameters that contribute, namely, yeah, we have a perturbing potential, so to say, if we want to do this in this grammatical approach. These are they look a little bit like Feynman diagrams, so to say, and you can put this into that language. We have this free propagator actually with the resonance, basically the resonance denominator that describes the resonance of the nuclei here, and we have a perturbing potential that comes about through the interaction of the photons with the mirrors here surrounding them. That is yeah, product of two quantities which actually contain the reflection coefficients here of the environment, and the optical, basically the index of refraction and so on, and a certain coupling coefficient. And then you sum up, yeah, d is the thickness of that layer. This is imaginary constant here, also relative phases between incident and emitted radiation into account. And Fn, that is the yeah, basically the nuclear scattering amplitude, which is proportional to that free propagator here. And so you sum up all this, and there is some arithmetic that actually I don't want to walk you through here, but rather than make you look at the result here. I will show that on the next slide again. So you get actually a modified resonance denominator here. If you compare it to the free propagator, then the propagator of the whole system looks like this, where actually the denominator is modified by a modification to the self-energy. So X is basically describing the resonant detuning in this basically Lorentzian spectral shape of that propagator. And you have a modification of the ensemble self-energy, a contribution correction to X, and you have a correction to the decay constant, basically, which is contained here in this dimensionless imaginary unit, of course, which is normalized to the natural decay time of the free nucleus. That's why this one is corrected here by the imaginary part of this perturbing potential. So that is the modification of the decay width. So actually what the cavity is doing to our nuclei ensemble, and here are the dimensions of the cavity mentioned. So you have a single layer reflectivity here, which is the natural line width of the IM57, basically, with this resonance behavior. And the cavity modifies this. The cavity modifies this, but maintains the functional shape. And that is the issue, the virtue of this eigenstate, of the property of the radiative eigenstate. It's still a Lorentzian, yeah. But the properties, the characteristics of this Lorentzian are different, much different. First of all, is shifted. So that is the calculation here for the spectral response of this cavity is shifted by a quantity that we call the collective lump shift, because it's basically, it refers to the exchange of virtual photons within an ensemble of identical emitters. Yeah, so the single atom lump shift is also it's going back to what's associated with the exchange, with the emission and reabsorption of virtual photons by the same atom. Here it is an exchange of virtual photons within an ensemble of identical atoms, the large ensemble. Yeah, and so this gives rise to this lump shift here, and we get this enormous enhancement of the line width here. As you can see from this curve here, compared to this narrow line of the single atom, of the single nucleus. So that is the collective lump shift, and that is the collective decay width, which reflects the super radiant emission property. Yeah, and that is also a formal manifestation of the fact that we have a radiative eigenstate here discovered of the embedded ensemble of emitters in this cavity setting. So this is again what I have said, a summary of what I said before. That the modification, the decay is modified, so the exponential decay of a free atom is modified in this fashion that this decay width becomes a complex value with these two components, the real and imaginary part, describing superradiance and the collective lump shift. So that's what we have measured. It's more than 10 years ago now, but right after the first PQE conference that I have attended in 2010, we could measure this curve that I've shown on the previous slide as a calculation. This is actually measured on the sample like this. We have lump shift, collective lump shift of 9 natural line widths, very significant, and a broadening, a superradiant broadening of almost 2 orders of magnitude compared to the decay width of a single nucleus. And this is the energy spectrum. So we have some modification due to residual hyperfinite actions, but that is doesn't impact the result here. And on the temporal scale, you see the enormous acceleration of the decay, superradiant decay, compared to the natural decay here. This leveling off that comes due to this residual hyperfinite action, which actually is introduces some slight deviation from this two-level property of that system. So yeah, this was measured actually in Grenoble at the European Synchronous Radiation Facility, ESRF, and it was picked up sort of by the science writers at the PR department, and they described this in a short way here, and then they tried to illustrate the lump shift. And what is the lump shift? That's for the ESRF, the lump shift was like this. The lump shift has been observed en masse. Yeah, so okay, we can imagine that people think about who don't know Willis lamp actually may think this look like this, but okay, this is obviously a misconception. But it's funny in the first place, but of course, yeah, maybe it catches your attention if you see such a picture in a science magazine. Anyway, a better approach is this one here, and this is actually a picture that I proposed for the cover of the science article, and it was actually taken. Which reflects much better actually what happens in the cavity. So this is a bottle of wine placed between 2 parallel mirrors. Yeah, and then we all know, especially if you go to a barber shop, for example, and the barber actually places a mirror behind your head to show you the back of your head. Actually, you sometimes see these multiple reflections going up to infinity that multiply whatever is in between these 2 mirrors. And that's exactly the setting that we have with the nuclei here in our cavity. So the X-rays go infinitely many times, and each nucleus basically can, or the nuclei can participate in the scattering, can contribute to the scattering process these multiple times actually until these amplitudes are eventually damped out. Yeah, you can then even extend this concept. Oh, wait a second, this label here says Chateau lamp, so maybe there is a Chateau lamp somewhere, but of course we could not use a commercial brand here for obvious reason. So that's why the DESI PR department developed a new label here and called this Chateau lamp. I like this very much. So they can put this forward actually and think about actually a new configuration where you have started to drink this wine here. Of course, this also is a nice illustration. You have virtual copies here. These are not real copies, of course. You still have a single bottle of wine, right? I mean, this you have to be aware of. But you can drink this wine and then also put your glass here on the side and also multiply this here several times. There's other ways. Another way is actually to direct the beam of a laser pointer between 2 parallel mirrors, and when it's dark outside, and you get these remarkable multiple reflections that eventually look like this here. And this went on to a cover of Nature Photonics, actually about an experiment that I'm going to talk about a few slides later in the field of quantum optics with X-rays. So
just one more question: why wine? I mean, is there anything more to the wine than?
I can't very. The voice is not coming through, Arne.
Okay, I'm sorry. Just 1 second.
Maybe that's better.
No, that's much better.
I just was wondering what's the significance of the wine bottle? I mean, like, could be anything, and you even had to come up with a label for Chateau Lamp.
Yeah, I mean, the wine bottle was accidentally, because when I came up with this idea at home, I just grabbed a wine bottle from my shelf and put it in between. So, yeah, I mean, you can actually, I mean, the wine can be taken as a sort of population of levels, and you can then think of pouring the wine into the neighboring glass. It's a population transfer of excitation energy from one side, one thing to the other here, for example. I mean, it's, of course, yeah, it's just a graphical, it's a graphical way to illustrate this. It could have been done with any other thing, but the wine bottle was just the accidentally victim, so to say, for the first shooting of the photo, and then the art editor of Science actually she liked it very much and took it. So that's it. And all right, yeah, but this photo was taken with a more serious background. I mean, these were two plexiglass plates actually here that are symbolizing two ensembles of emitters between these two parallel mirrors. I will show you on one of the next slides. So I think I should speed up a little bit due to the time that has advanced. So this was then a sort of perspective article by Marlan and Anatoly Svidzinski written about this, our paper, and which actually explains in a better way, instead of the lamps that were shifted, what this cavity is about. So yeah, controlling cooperative emission in the cavity really determines the radiative properties of the embedded emitters. That is the lesson that we learned. So we can actually now put one more layer actually into the cavity, and the radiative properties are determined by the number density of the atoms inside the cavity, how thick the layer is, and at which place actually these are located. So it matters actually in this this wave field inside the cavity, which constitutes nodes and antinodes. So in the nodes, actually the photonic density of states is small, and the antinodes it's large. So we get a strong superradiance here in the antinodes and almost subradiant situations in the nodes. And that allows us to actually have different couplings of these two ensembles to the cavity field. So with two decay widths, actually, here's the ground state, here are the superradiant state, here's the sort of almost subradiant state comparable to a metastable state. You have the cavity field as a control field, and essentially you have a three-level system that resembles that of a lambda system of EIT. And that is actually what happens. I mean, the cavity converts the iron 57 nuclei all of a sudden into three-level systems. Yeah, so just by inserting these two ensembles here, we can engineer these level systems and observe an analogon basically of EIT in that system. Of course, with a completely different way to establish the control field, but nevertheless, it worked out here, and that is the dip that actually the transparency dip that we observed here. So here we have a coherence interference between different excitation channels, and the idea was then put forward by Jörg Evers' group in Heidelberg, who I'm collaborating with, to also use these cavities to establish coherence between emission channels. And these are these so-called spontaneously generated coherences that show up here as deep deep minima in the spectral dependence of the scattering. Okay, one can then put this further forward actually by coupling those cavities to each other and reach a level that is really coming close to strong coupling with normal mode splitting and Rabi oscillations. So here we have a nuclear superlattice, actually many cavities, resonant layer cladding, multiplied many times as a superlattice. We observed a normal mode splitting of 8 gamma naught. Here I can want to briefly touch it here, which is basically a photonic bandgap material, essentially. Or if we look just onto 2 coupled cavities, we can then also really see also the temporal version of this normal mode splitting, namely the Rabi oscillations, the periodic energy exchange between 2 nuclear ensembles in these coupled cavities. This actually was also put forward then by my graduate student Johann Haber here. He was the first author already of those publications to apply this not to a nuclear resonance, but to the tantalum L3 edge, where we also could observe the lump shift, the collective lump shift here in the shift of the white line absorption, the absorption line near the L edge of tantalum. So that's not a nuclear, that's an inner shell resonance, which is relatively strongly peaked, and we could clearly see the shift of several EV that also changes sign if you go across a critical coupling angle in the cavity. So you can then imagine, I mean, that is also quite a modern research field now to employ cavity to influence the light matter coupling and also modify electronic transitions actually by coupling photons into these systems that are embedded in cavities here. I just want to mention this here as a research field that is really flourishing these days and may find applications also for controlling and manipulating electronic transitions. So that is basically a summary of what I've said before. I think I keep that short here to just briefly scratch actually the one item of my title, namely quantum imaging, which is actually an extension actually of Henry-Brown twist starlight intensity interferometry to X-rays. And this, I think I don't have to explain HPT, the HPT experiment. This actually correlation type of experiment, intensity correlation type of experiment was then put forward by, amongst others, certainly by Joachim von Santier in Erlangen, who I am working with, not in this experiments, but on those here on the right. He, before we met each other, he already has established this multi-photon super resolution intensity interferometry, which is actually putting forward this idea to higher order correlations, which he published in a number of papers. And after we met, we thought, why don't we get together and put this concept forward into the regime of X-rays? And this is actually what is shown here on this slide, where we use intensity correlations of X-rays to determine the structure of an object. So how does that work? So the basic idea of HPT interferometry is, of course, to determine the diameter of of a star by measuring the intensity, second order intensity correlation as a function of distance of 2 detectors that were recording the light from the star. And Henry, Dawn, and Twist recorded such a curve here, which is a second order intensity correlation from the width of which they could determine the diameter of the star. So that was actually a structure determination experiment in principle. So intensity correlations are able to reveal structural information. And if you take this literally, I mean, you can imagine that also different arrangements of scatterers actually can be employed to this method. And this is indeed, we have shown that this works. The prerequisite is, of course, that the detection has to take place within time intervals that are shorter than the fluctuation time. And these short pulse laser sources, actually, they provide a very fruitful ground to establish this concept. pulsed sources of hard X-rays. They really enable this, because the pulse duration provides a natural time gating to fulfill actually this condition here. That is at the heart of this intensity interferometry. Because if you have two emitters here, for example, you in principle can have a far field interference pattern if you have a well-defined phase, but if they emit incoherently, each emission act is taking place with different relative phases, and then what you record on the far field interference pattern is just a straight intensity. That is incoherent emission. Incoherent emission are emission acts from single emitters that where the relative phases, say, of two emitters is really statistically fluctuating, and on the average you get a homogeneously illuminated screen. While if you take these intensity patterns within the correlation time, within the emission time of the emitting atoms here, you always have, you record a far field interference pattern, and you can take the intensity autocorrelation, which is independent of the fringe shift, of the shifted fringes that I have shown on the previous slide, and this contains structural information. So if you take many of these intensity autocorrelation functions for taken recorded within the short emission time, with matching these conditions for temporal comparison of emission time and recording time, then you are able to determine the autocorrelation function and average over them. So, for example, in 2 dimensions, this works as well. You have these 2-dimensional emitters leading to a far field diffraction pattern like this. You have another situation where other atoms are excited and they emit also with random phases, giving a different far field diffraction pattern, and so on and so on. And each far field diffraction pattern contains the same structural information function, so structural information, so from which you can then retrieve the structure of the emitting object. That's actually what we have done at an experiment at Flash together with Joachim. And the object was a hole mask of 6 holes here, or rectangular holes in this mask. And from the analysis of these far field diffraction patterns, also towards higher orders, larger than 2 intensity correlations, we could really determine the spatial frequencies that make up the structure here, and we could really retrieve this structure quite well from this experiment. That actually made us optimistic to put this idea forward to 3-dimensional structure determination from objects like crystals, and this is what we worked out. This was the Flash experiment here, as shown on the previous slide, and this is a theory paper that worked out this idea here to use fluorescence radiation, incoherent fluorescence radiation from metal atoms embedded in crystals, for example, these inorganic metal organic enzyme ferrodoxine that has a iron sulfur cluster here embedded in, and this fluorescence radiation then could be used as means to for structure determination by intensity correlation. And this is this is the relation of the second order correlation function with the structural amplitude, with the structure factor of this sample of the diffracting object, the really short X-ray pulse from a free electron laser that is actually in the range of the emission time, of the fluorescence emission time of the metal atoms here in that crystal. So this matching actually makes us optimistic that to achieve this goal, to use intensity correlation from the fluorescence emission to retrieve the structure of the scattering objects. That can be combined, of course, with coherent scattering as a second means of information to really put these together to retrieve really high resolution data from those entities here. So this is a number of advantages. Maybe I don't discuss them here in detail. One is, of course, as you see here, just one. We have a much larger coverage of reciprocal space with this method compared to coherent diffractive, the conventional method of X-ray diffraction, because we have this large area pixel detector here where actually all these points, 2 points chosen, actually define one momentum transfer actually that can be evaluated and taken for structure information that is contained here in this structure factor. So that's actually simply due to the geometry of the experiment and the principle setting this huge coverage of reciprocal momentum space in this method. Yeah, so with this, I'm really coming close. I'm at the end of my presentation here, and want to not close without thanking my coworkers here. So there's a huge, over all the years, a huge number of groups that have participated here. And my group at DAISY, different groups at the synchrotrons. Here at Jena, I'm working together with these colleagues. I didn't mention what we have done here on X-ray polarization analysis, for example, theory support from Jörg Evers and Adriana Palfi in Heidelberg. Joachim, of course, I mentioned already, and the continuous inspiration by Marlan and his co-workers. Eventually, we got funding in this joint venture, the Collaborative Research Center, CUCO Lima, Quantum Cooperativity of Light and Matter, where many further projects are embedded, and we have funding since the beginning of this year, where Mainz is also one university partner in this TRR. And finally, I want to thank you very much for your attention, and I'm open for questions now.
Well, thank you very much for this excellent talk, Professor Röhlsberger. It's quite impressive, the results. Well, the talk is open now for discussion, questions. Yeah, please, Dima.
Thank you very much. This is amazingly interesting talk. I actually have more of a comment than a question, that in order to excite low energy nuclear transition, synchrotron radiation is great, but there is another approach that is currently discussed in the context of gamma factory at CERN, which is to put partially stripped ions in the LHC, which has been demonstrated that it works. And then you take a normal optical laser and as seen by the relativistic ion, the energy is shifted by twice the relativistic factor. So you can excite up to 60 kilovolt and then perform spectroscopy of these nuclear systems that way as well.
Okay, so that is due to the high Doppler shift, basically, right?
Yes, a relativistic Doppler shift, exactly.
Yeah, okay.
Yeah. So that's a bit complementary to what you were describing, but
yeah. So yeah, that's of course, yeah. I've heard about this approach that was many years ago still discussed theoretically, but I didn't know that it is now being about to be realized. Do you have already results?
Is, that these partially stripped ions are have been circulated and shown to have long lifetimes. And now the next step is still a proposal, but hopefully will be approved soon.
Yeah, I'm looking forward to see some results in that direction. So please let me know. I mean, if there's
absolutely
breaking news. Yeah, thanks.
But Dima, how would the luminosity or the compare to what Ralf discussed?
Yeah.
Do you know? Do you have an idea?
I think it would be pretty high, and also the gamma factory. Sorry, one second. Gamma factory. The main goal of the gamma factory is to actually generate secondary photons that are. So you excite well an electronic transition or a nuclear transition, and then the rescattered photon as seen in the lab frame has another 2 gamma energy boost, and this is the production of such high energy photons up to 400 MeV is the main goal of the Gamma Factory, and the fluxes there are very, very high. Projected fluxes are 10 to the 17 photons per second. So at energies which are much higher than the synchrotron radiation sources.
So, but this is then intended to break up a coupling of nucleons in the nucleus, right? And
yeah. So then those photons can be used already even for particle physics, but also for high energy nuclear physics. And this is the 400 MeV sort of the upper limit.
Yeah. Arne?
Yeah, super nice talk, and a gigantic amount of Nature publications, so no, congratulations to that. I was just wondering how you design your cavities and what the properties are. I mean, like, because normally you have a mirror and another mirror, and then you can move them around, you can tune them, but I assume that's nothing that you could do. So what are your cavity properties?
Yeah, I mean, these are thin film cavities of say layers a few nanometer thickness, and of course, we have to deal with the fixed distance of these layers, but in principle we can tune the coupling by in the vicinity of the critical coupling, so to vary the coupling by tuning the angle of incidence. That is possible. We can actually go to different modes. I mean, if the cavity supports, if the guiding layer is sufficiently thick, it supports many modes that are actually then can be selected by respective angles of incidence, and where of course the coupling of the radiation field to the nuclei can then be varied. Yeah, so that is possible in a discrete fashion, so to say. And this in some sense would replace actually the way if you mechanically change the distance of the cladding of the mirrors to some degree. Yeah, so it has in principle, if one puts some more effort in, one could also think of designing really two mirror systems with a vacuum spacing in between that are moved by piezo motion, for example, relative to each other, where we can then couple the radiation into and not put the nuclei into the center of the guiding layer, but rather on the mirrors itself. This also, the coupling is not that strong then, but the phenomena and the fact that we have radiative eigenstates is still there. Yeah, so that would be something for the near future, but it's a challenge to design systems, macroscopic mirror systems, say with square centimeter or at least square millimeter surface area, and move them in a plane parallel fashion with sub-nanometer precision. But it's not impossible.
And what's the finesse, or do you think in finesse of your cavities?
Yeah, the finesse, I mean, the finesse is not outstandingly high. I mean, we have, say, a maximum finesse of 100 or so. Yeah, so it's still, we are in the quantum optics term, we're still in the bad cavity limit that we have to admit. But it's not so much the finesse actually that we are using here, but the fact that we have this geometry, the single radiative eigenstate because of the equal phases between the emitting nuclei. That is actually the qualitative highlight, so to say, of this cavity setting. Not so we cannot compete with optical cavities that have finesses of whatever 10 to the 9 or even more. I mean, that we are far away from that we have to admit. But okay, we can prepare and control these eigenstates, and in this way generate say new coupling schemes of two-level systems to a radiation field.
Good, thanks.
I see there is a raising hand. Joseph, please.
Hi, thanks for a nice talk. I was a bit, I want So my question is based on the lamp shift that was discussed. I was under the impression we are addressing nuclear states, and my mind went into a concept that there is a separate nuclear lamp shift. Is that what you're implying, or is it just the same lamp shift that we are studying in electronic states?
I mean, it's a different one, of course. I mean, we cannot. It does not compare directly to the lamp shift that you know from, say, atomic hydrogen or so. Yeah, I mean, this is that's a lamp shift of bound. I mean, that is a generic feature. I mean, you observe, say, a shift of level shift, a general level shift of quantum systems that are bound into a system, for example, in this atomic system, an electron to the coupled to the nucleus. This already leads to exchange of virtual photons of this bound systems with itself, so to say, and this is of course, yeah, known also in heavy atoms. Uranium, for example, the lamp shift is much larger, several electron volts. But here we have, exchange of virtual photons, not within the same atom, but within an ensemble of identical atoms. So if you say consider a virtual photon that is emitted for a short time from a nucleus that can then be reabsorbed by another atom in that ensemble, and all these different possibilities you have to sum up over, and you then eventually arrive at that expression for that collective lamp shift that I have shown. So it's of different character. It can be also considered as a correction to the dipole-dipole coupling of the emitters and so on. But and many people say, okay, yeah, that's dipolar coupling correction, and criticize the name lamp shift, so to say. But I mean, for me, it's actually this version of virtual photon interchange that justifies this name that was actually introduced by early theoreticians that were dealing with this. So from that, it's a different character than in single atoms.
Okay. Thank you.
Any other questions or comments? Actually, I have one small one. It concerns this imaging part. What I would like to ask, how many snapshots you would need for extracting the structure of the sample by analyzing these correlation functions?
Okay, yeah, good question. I mean, in that experiment that I have shown, these were averages over 10,000, 15,000, 20,000 exposures, pulses from flash. Yeah, so this was a number of pulses. Of course, we have a repetition rate of 10 pulses per second, actually. So it was maybe a few hours of data acquisition time in this example. But okay, that was also needed to gain a sufficiently large intensity and statistical quality of this autocorrelation function to retrieve actually the spatial frequency with sufficient precision. But I mean, it's at a high rep rate facility. I mean, this is easily met. I mean, 10,000, even 100,000 pulses are actually taken in a short time.
Yeah, thank you. But then it would be, I mean, this kind of investigations can be done on solids, for instance, not on cells, on biomolecules or something like that, because then you would destruct them, right?
Right, yeah. I mean, this, there, of course, are some conditions to be met, yeah. In principle, I mean, with a sufficient monochromatization of the X-rays and the optimized setting, I mean, in many cases, this these conditions can be met, or you just manage to prepare your quantum systems in always the same orientation and state when you insert it into the beam. So, but this is an activity that is pursued by many groups and has been successfully shown already in many instances. For example, you can insert, particles at random orientations into the beam and simultaneously record the coherent diffraction pattern, and then sort your data afterwards and take only those data sets where the crystal was actually in the same position, in a position that you had that you have selected, or you can select and bin all the data according to the orientation of the crystal by analyzing the coherent diffraction patterns simultaneously. That is also possible. So by a kind of post-selection approach. Data analysis is really a challenge in that field, but if the principle, we are already happy if we are able to show the proof of concept, and then of course technology has to follow and ensure that that these ideas can be really put into practice.
Okay, thank you very much. Any further questions, comments? Okay, I don't see any raising hands. We would like to thank you, Professor Ralf Röhlsberger, for this nice talk. And with this, we would like, before closing this session, I would like to announce the next speaker for next week. It will be about Pauli blocking of atomic spontaneous decay by Dr. Christian Sana from Jena and the University of Colorado in Boulder. Thank you very much for joining this session, and see you